Okay, so we're going to talk about work today. So we have some preliminary sort of physics-y things to talk about. Work is force times distance, and weight is the force that gravity exerts on an object of particular mass. So weight is generally equal to mass times the acceleration of gravity. So mass, the English unit for mass is a slug, and the metric unit is a kilogram. And you never hear the word slug because when we talk about the force of something in English units, what do we usually use? English units that is not, it sort of measures mass, but not really. Pounds, yeah. So pounds is the unit for force in English units. Right, so that's why we have pounds here. So mass, slugs, and kilograms. Force, the units are pounds and newtons for metric. And Newton is just a kilogram times a meter per second squared, right? Because force is mass, kilograms times acceleration, meter per second squared. We call that a Newton. And then work is force times distance. So work, we have a unit for distance and a unit for force. So in the English units, we call it a foot-pound. And in metric units, we do newtons, which is a measure of force, times meters, which is a measure of distance. So we either say Newton meters, or another word we have for that is a joule. All right, what is the weight of 1 kilogram of iron? (9.8 newtons). Yeah, right. So weight, remember, is mass times acceleration. So we've got mass. So weight is mass, 1 kilogram, times acceleration of gravity, in this case 9.8 meters per second squared. And we end up with 9.8. What's my unit? Newtons. Okay. All right, how much work is done lifting that 1 kilogram piece of iron 3 meters off the floor? So we have to remember work equals force times distance. Okay, so what is my force? (9.8 newtons). Yeah. The weight of an object is also just sort of another way of saying the force. So my force is 9.8 newtons. And the distance I'm moving that object is 3 meters. So it's 9.8 times 3 Newton meters, which is also known as a joule. (29.4 joules). Okay, so we haven't done any calculus yet today. Should be a little red flag. This is going to get harder, right? So say we have a 45-meter rope. Its mass is 30 kilograms. It's dangling over the edge of a cliff. Ignoring friction, how much work is needed to pull the rope up to the top of the cliff? So here's a solution, right? I wrote down work equals force times distance. Force is 294 newtons. Where the heck did I get that? (9.8 times 30 kilograms). Yep, 30 kilograms is mass times the acceleration of gravity gives me force of 294. All right, so we'll just say aside here, force is 30 kilograms times 9.8 meters per second squared, which is 294 newtons. Okay, so force times distance, I did my 294 newtons times 45 meters that I have to pull the rope up, and I get 13,230 joules. What is wrong with that solution? Right. Each piece of the rope has to move a different distance. Yeah. So once I pull part of the rope up, I don't have to pull it anymore. I have less work to do. So what's wrong with this problem is that each point on the rope moves a different distance. Okay, so to get a true solution, I have to chop the rope up into little tiny teeny pieces, find the work performed on each little tiny teeny piece, add them all up, and then I will be performing what? When you chop something up into teeny tiny little pieces and add them all up and take a limit, you get an integral. Okay, so let's just draw a little picture. Here's my rope. It's the top of it, bottom. And the whole thing is 30 kilograms, right? I'm going to look at just a random little tiny, teeny bitty section of rope. And we're going to figure out how much work we're going to do to move that piece of rope up to the top of the cliff. All right, so I have to know how much force. So I need to know like the weight of this thing, which is its mass times 9.8. So what is the mass of that chunk of rope? Depends on how much rope we have. Okay, let's call this amount of rope delta x. That's the length of the rope, not the mass of that little piece of rope. Total mass is 30 kilograms, yep. An integral of what? So we know the total mass of the rope, right? And we know the length of the rope. So the total mass is 30 kilograms and the length was 45 meters. So if I do 30 kilograms divided by 45 meters, what is that? 2/3 kilograms per meter, right? So each meter of my rope is like 2/3 of a kilogram. How many meters do I have drawn in that little teeny bit there? Pink highlighted part. How many meters long is it? Delta x. So if I want to know its mass, I could take the 2/3 kilograms per meter times the number of meters. Right. So the mass of my, we'll call it a slice, it's going to be 2/3 kilograms per meter times delta x meters. Right, so my meters are going to cancel, and I'm going to end up with 2/3 delta x kilograms. All right, so there's my mass of the little chunk of rope, little tiny slice. So what else do I need for finding work? I need force, which is mass times acceleration. So I'm almost done here. Now I need to find the force of gravity on this slice, which is the mass times the acceleration. So it's just going to be 2/3 delta x times 9.8. So we'll call that 98/15 delta x. And what are my units on the force? Newtons, thank you. Okay, so now I know the force on that little tiny teeny chunk of rope that just has length delta x. I need to know how much work is performed on that little tiny teeny chunk of rope. So work is force times distance. So I just need to know what distance that little teeny tiny chunk of rope travels, and I'll be able to find the work. All right, so let's put this chunk of rope at a distance of x from, the whole thing is 45, right? So how far does that have to travel? We'll call this, we should label this 0 will be at the top. And then this is at x, and this is at 45. So it has to travel x meters, yeah. All right, so my work done on my slice is force times distance. Force was 98/15 delta x. Distance is going to be just x. And I'm just going to simplify it a little bit, so it's 98/15 x delta x. So that's the work done on just one little bitty piece of the rope. So to find the work done on the entire length of rope, I have to add up the work done on many, many little slices of rope. Right? Just do this exact calculation many, many times, add them all up, and when you add them all up and take a limit, you're going to end up with an integral. So my work total is going to be an integral of the where each term in my sum looks like that. Okay, so it'll be 98/15 x, the delta x becomes a dx, and I'm going to integrate from where to where? 0 to 45. The x value, this random x value that I put on the rope, it ranges from 0 to 45. All right, so this is not too hard an integral to calculate. This is 98/15 x squared over 2, evaluated from 0 to 45. All right, so 45 squared times 98 over 30, and I get 66/15. And when I plug in a 0, I'm going to get 0. So I have 66/15, and my newtons for work are joules. I know. Yep. So Newton is a measure of force, joule is a measure of work. So one thing that can help you is to try to keep track of the units of all the different expressions in your integral. So your 98/15 delta x was newtons, right? So we took a moment here to figure out, to remember what the units were there. 98/15 delta x was newtons. And so then when I went down here, the 98/15 plus the dx, right? So these two things went together, and when I multiplied them together, I got newtons. And x was a measure of distance, so that's meters. And a newton meter is equivalent to a joule. It will definitely just take some practice and getting used to the fluency of. Oh, okay. Good. All right, so does this make sense? Go back down, sure. All the way up. So it's the same basic premise that we've been doing for several classes now. Chop it up, find the thing you're looking for on each little piece, and then add them all up, and you get an integral. We have a water tank in the shape of a right circular cone that has height 1 meter. The radius of the top is 1/2 meter. there's a column of water in this cone that has a height of 0.5 meters. We want to find the work that must be done to empty the tank by pumping the water over the top edge. And you do need to know that water has a density of 1,000 kilograms per cubic meter, which means that if we find its volume, we will know its mass. Okay, so I can't just do one calculation for all of the water because different pieces of the water, like water at this height, will take a certain amount of work to pump out, and the water that's lower down will take more work to pump out. Or it has to go further. I don't know if it will take more work because there's less water down there. But we're going to have to calculate the work to pump out slices of water, right? Just think of the water as being sliced horizontally, and we're going to pump out a slice at a time, figure out the work done on each slice, and add them all up. All right, so let's have this, make this sort of an axis. We'll have this be 0 and this be 1. Okay. And I'm going to pick a slice at a random height of x. All right, so this slice, I have to figure out how much work I do to pump the water, that little teeny slice, out of the cone. All right, so that slice is going to have, look like a circle, and it has a little bit of thickness. And what variable should that thickness have? Delta x, yep. And then I need to know the radius of that slice if I want to know the volume of the slice. Okay, so we'll call that r, which is what I need to know. How could I figure out that radius r? Similar triangles, yeah. Great. So I have this large pink triangle, and then I have this little blue triangle that are similar to each other. So I could say the radius of the big to the radius of my little, 0.5 is to r as, then what other two measurements can I use? 1 is to x. The whole height of my pink triangle is a 1. The height of my little blue triangle is x, because I put that at a random height of x. And then I'm just going to solve this for r, because I want to be able to replace r with something with x's in it. So r is 1/2 x. So I come over here, replace the r with 1/2 x. Okay, so the volume of this slice of water is pi times the radius squared times delta x. So but what I need to know is the mass of the slice. And we talked about this a couple classes ago. If you know density, you get mass by doing volume times density. Because my volume units are cubic meters, right? And so if I multiply by kilograms per cubic meter, I'm just going to come out with kilograms. So the mass of my slice is the volume in cubic meters times the density in kilograms per cubic meter, which will give me kilograms. So I just have to take this volume calculation that I did before and multiply by 1,000 kilograms per cubic meter. So I'm going to have 1,000 pi times 1/2 x squared delta x, mass of my slice. Just took the volume of my slice and multiplied by the density of 1,000 kilograms per cubic meter. And then I guess I can simplify this a little bit. So 1/2 squared is 1/4, and 1/4 of 1,000 is 250. Okay, so I get the mass of the slice. Now I need the force of gravity on this slice. I need to calculate how much force gravity is exerting on this slice of water, and force is mass times acceleration. So the force of my acting on my slice is the mass 250 pi x squared delta x times acceleration of 9.8 meters per second squared. Oops, 250. So 250 times 9.8 is 2,450 pi x squared delta x. And the units on force are newtons. All right, so I'm just calculating one piece at a time with the information I have, right? First, calculate the volume of a slice. Use that to get the mass of the slice. Use that to get the force of gravity acting on that slice. So now that I have force, I just need distance, because force times distance will give me work. All right, so the work done on my slice is going to be the force done on my slice times the distance that that slice moves. Okay, so force I know is 2,450 pi x squared delta x. And then how far does that slice have to move to pump it out of the cone? 1 minus x, yeah. Because I happened to label the 0 down here. You can label it differently, and it should come out the same. It's just going to change your calculation a little bit, and you'll end up with the same answer. But the way I labeled this, I have to move this 1 minus x to get the slice out of the cone. 1 minus x meters. Then I just have to add up all my slices, and that creates an integral. So my total work is going to be an integral where I'm adding up all of these slices that have where I do this much work on each one. So write it like this: 1 minus x, distance we have to move it, and then I have times 2,450 pi x squared. The delta x becomes a dx when we take the limit. And then my bounds of integration for the x, right? What value to close? 0, not to 1, but no, 0.5. Because the slices are only being stacked from 0 to 0.5. Right? We're pumping them a further distance, which was why you have the 1 minus x. But the x's, this x variable, represents the height of the slice in the cone, and those slices only go from 0 to 1/2. So I'm going to integrate from 0 to 0.5. And if you had, again, if you had drawn the picture differently, the bounds of integration might be a little different, and the distance that the slice travels is going to look a little different, but your answer would come out the same. Okay, how would I evaluate this integral? What do I do? Multiply it out, and then it'll just be a simple power rule problem. So I'm going to distribute the 2,450 pi x squared. and then it's just a power rule problem. So my antiderivative of the first term, 2,450 divided by 3. I'll just leave it 2,450 over 3. And then the antiderivative of the next term would be 2,450 pi x to the 4th over 4. Uh, 612.5. So there's my antiderivative, and then I have to evaluate that from 0 to a half. Okay, so if I plug in a half, 0.5 cubed times 2,450 divided by 3. That's 1225 pi over 12. And then I have to plug a half into the next term, 0.5 to the 4th. Oops. Times 612.5. $12.25 pi over 32. Okay, so that's what I get when I plug in a half, and when I plug in 0, I get 0. Because every term has an x in it. So I just have to do the subtraction. 1225 over 12 minus 1225 over 32. Oops. 6125 over 96. Okay, so there's my exact value, and if I want an estimate, I just multiply by pi. 200.44. And my units on work are joules. Questions? All right, I'm going to let you try some.